person. So I'm here. The talk is on the direct measurement of cosmic rays. I'll make a review and discussing what we are learning from the recent measurements. We know that we live in a very good epoch for cosmic ray measurements. Maybe not for other things, but for cosmic rays, we are in a era where lot of new and high quality data are coming. Here is just a few pictures regarding the experiments that are more discussed in this talk, but maybe better here. This is a kind of timeline of since the beginning of the millennium, how it started and how it's going, and it's going pretty well. Several of the direct measurements are now being done in space experiments, and there are also interesting and pioneering projects on balloon. So there is really a lot of new measurements to be discussed. What we have established in the decades is a paradigm for cosmic rays, which is our understanding. It's based on three main pillars. The idea that they come from galactic sources and they are shock accelerated. This is followed by diffusive propagation with collision with the gas and production of secondaries. This very simple picture led to very basic predictions that we are not going to see in the details, but from this, what we used to expect for a long time is essentially a power law paradigm. Power laws everywhere, in the acceleration spectrum, in the propagation, in the diffusion coefficient, and in the spectra of secondaries. The models built on this idea for a long time relied on several simplified assumptions concerning the dimensionality, the homogeneity of the gas, of the diffusion, the isotropicity of diffusion, the steady state, the linearity, etc. But now we have several data that are continuously challenging our paradigm, or maybe we are realizing that the paradigm is itself more complex than what we liked to believe. There were classical outstanding questions of cosmic rays related to their origin, and to their sources, the properties of the sources, like the composition, what's the acceleration spectrum, what's the maximum energy of the sources, and how their propagation works in the galaxy. And now we will see in relation to all these questions what we are gaining under in the history that comes 12 years ago, more or less. We had many new data and a long series of anomalies. One important one was the discovery of this spectral hardening, or the breaks in the spectra, in the proton and helium spectrum at about 200 or 300 gigavolt of rigidity. This was realized first by Krim, Attic, and clearly shown from the Pamela experiments, where the spectrum of cosmic protons and helium were clearly subjected to a change of slope at about 200 gigavolt of rigidity. And this was clearly unexplained and challenging the paradigm where everything is power law distributed. It was a clear break in the spectrum, and also later measured very well by other experiments. Here is the helium spectrum multiplied by 2.7 from the AMS experiment in space. There are new questions regarding this? What's the origin of these features? And is these features universal features of all nuclei, or just depends on the elements? Along with this, the ratio between proton and helium was found not to be constant in as function of rigidity. And yeah, I show in the left old plot by Weber of the 79, where the data and concluded that the spectra universal, so at the same spectral index. And this universality was tested, but also assumed to be true until 2010, more or less. Then we had the proof that at least proton was remarkably steeper than helium. The right plot is enter the PDG, the particle data book, the data group review in the booklet, and it's the AMS and Pamela measurement of this proton to helium ratio. Also, yesterday Vitaly Shutko shown the recent measurement was with the AMS. Not only it decreases, and we don't know yet why, but it has it seems to have a tendency to flatten in the very high rigidity part of the spectrum, which is also visible if we collect data in as function of kinetic energy from several experiments in the multi-TeV regions. So there is many questions arising from this observation and the hardening, the spectral hardening. Why the proton and helium spectra have different slope? Is this related to their acceleration or different sources, maybe, as suggested here? And why, in spite of different acceleration spectrum, the ratio is smooth, so that the hardening, the break is cancelled somehow in the ratio. And what's the origin of this break? Two different competing scenarios were related to acceleration on one side and propagation on the other side, with different predictions. If the acceleration spectrum is broken at some level, it has, and so the break is caused by the injection, by the acceleration, or by the multiple sources, maybe. In this case, we expect, of course, breaks in all primaries, and breaks in secondary cosmic rays inherited from the primaries. So similar breaks in all the similar hardening effect in all the species. In the case that in the right plot, the hardening is related to diffusion, we would expect a stronger hardening for the secondary spectrum, the red here, and thus a feature observable also in the secondary to primary ratios. Now we look at the data to clarify. What was found first is that this hardening is present in the most abundant primaries beyond helium is carbon and oxygen, measured by AMS and by Calet in particular, Pamela. We see clearly that there is a spectral hardening at the more or less the same rigidity of 300 gigavolt. There is also a persisting discrepancy between AMS and Pamela or Calet for both carbon and oxygen. But regarding the spectral shape, the consistency is good, and also the carbon to oxygen ratio is very consistent for the different experiments. Also in the multi-TeV regions, in the measurements by nucleon, the carbon and similarly the oxygen is seen to harden, to have a hard spectrum. Essentially the hardening is common to all primaries. What is interesting is to look at secondaries. And this is measurements by IMS of lithium, beryllium, and boron what we see in the left plot, they gather in different groups than in comparison to primaries, and the spectra are steeper, of course, and this is not unexpected. This is what we expect. Is remarkable here is the spectral, the change of spectral index in this secondary group, which is stronger. It's essentially the double change of slope in comparison to what was observed in primary. Or in other words, also, if we compute the secondary to primary ratio, like lithium to oxygen, beryllium to oxygen, or boron to oxygen, we observe a change in the ratios too, a change of spectral slope. This clearly shows that the secondaries have a stronger hardening effect, which means that should be the diffusion should be responsible for the hardening effect. And this should be an answer to the many questions. And from the data, it seems also conclusive answer. Also, want to show the data from Nucleon in the TEV regions and above, showing that secondary to primary ratios are indeed quite hard and don't show the traditional rigidity dependence, which was very fast decreasing when they used to be measured only in the JeV, 10 JeV scale. Now with this, actually, with the EMS and Calet in particular, recently many species were measured, and other anomalous behavior were found. So it's not the end of the story. And silicon with the spectral indices in the left, and in the right, we see that the species tend to form by the spectral point of view of a different class of nuclei that are harder by some factor in comparison to helium, carbon, and oxygen, which is the primary class. Sorry. Okay. And this is to be explained. But what we see here is that there is a group of intermediate mass nuclei that has harder spectrum. Could be related to different sources where they are accelerated, so different compositions, and or could be some unknown effect in the acceleration that depends on the mass. Another path-slim feature was related and shown yesterday by Vitaly Shutko to secondaries. If we see here the fluorine spectrum, the fluorine is entirely secondary elements and was in the past not much discussed because the data were mostly focused on boron and carbon, or boron to carbon ratio, while fluorine is poorly known because experimentally challenging to measure. Also to model because the production cross sections are not very well known. Anyway, the spectrum looks great. It's a secondary element. It has a spectrum decreasing faster with energy, like a secondary nuclear does. But if we show, for instance, the fluorine to silicon ratio as function of rigidity, there are two features. One is there is a break, which is not different to what we noticed before in the, for instance, in the boron to oxygen ratio. A break about 200 gigawatt of rigidity with a change of slope. But essentially, this ratio is harder in the whole range in comparison to the boron to oxygen ratio. So it's a different class of secondary primary spectral point of view. There is some difference to be understood. This is another open question. Other puzzling results are on the intermediate nuclei like sodium or aluminum, and comparing them to nitrogen. These three are of mixed origins. Some part of are in the sources, but they are strongly enriched by secondary components, so that the spectrum should be described as a mixture of secondary and primary components. And the strange thing is this mixture is different from element to element, and is not correctly reproduced by the standard propagation models. Of course, it depends on the abundance of the fragmenting primaries and on the cross sections. Maybe it's something to be understood in this fragmentation chain, but it's hard at the moment to reproduce this spectra. Also, the spectral behavior is puzzling. If we see above the sodium, the sodium looks similar to nitrogen in the low energy part, but not in the high energy part, while the aluminum is becomes consistent with nitrogen only in the high energy part. Then the iron spectrum is measured very precisely by AMS and Calet in particular. And it has some also some puzzling feature. The spectrum in general is hard to be modeled for several reasons, but it's not understood what's wrong with iron. What AMS found was shown yesterday is that the iron spectrum is, of course, cannot be considered a light component, because we have the light group, helium, carbon, oxygen, then a heavier group like silicon, but of primaries. But it seems that the iron spectrum behave more similarly to, by the spectral point of view, to the light component. If I go, sorry, in this plot, there are two, by the spectral point of view, two classes of primaries, maybe related to their sources. One is the light and the helium, carbon, oxygen, and one is the heavy component, neon, magnesium, and silicon. And it seems that the iron spectrum is more similar to the lighter. This is quite puzzling. By AMS and by Calet with incredible precision, we now know that the nickel at very high energy exists, of course, and it has a rigidity dependence very similar to the one of iron. What is true for iron is essentially for nickel, with of course 20 times smaller abundance. So there is regarding this summary complex picture with many unexplained features. These two classes of primaries, the secondary of fluorine, which seems to belong to a harder component of secondaries, and the mixture, the mixed components, primary plus secondary of intermediate nuclei that that is not described very well. And in general, every nucleus seems to have a different, every primary, different spectrum, not only as we observed here, but at the injection level. This is, of course, could be unveiled only with a propagation model and framework. But this is what it's found. It's found the paradigm of universal spectral indices, not only at arriving Earth, but at acceleration level, is now broken. There are also claimed some other anomalies regarding the very low energy part, the low energy part of this spectra, where it seems that the presence of extra local source is manifesting, and this is was claimed in the aluminum, in fluorine, and in iron, where at least using the Galprop framework and the Helmholtz modulation framework, it becomes clear in this case the evidence for having a additional source term. The presence of a local source is actually also expected somehow for other reasons related also to the observation of isotopes and to the local bubble. The effect of such a local source in the cosmic ray spectrum is not obvious. There are hints, many hints for having some low energy signature, but in the other side, in the high energy part, we have some other features appearing above the high energy hardening at 100 JeV. Above TeV, it gets softer. It was hinted in various data and shown in CRIM data, nucleon data. And now with the Calet and Dampe, it's now clear that there is a new feature at about 20 TeV. This is from ISS CRIM. At about 10 TeV, there is a softening was reported. This is the data from Dampe, where the proton spectrum multiplied by 2.7 shown a break at about 10-20 TeV, and a similar break or softening is reported in the helium spectrum. So the origin of this is not clear. It could be the effect of a local source. It could be, it's unclear, but apparently this effect is there. So it's not even the spectrum a broken power law, but it isn't a power law anywhere in some sense, because every decade we have some anomaly in the cosmic ray spectrum. That's our current understanding. There is also, I want to mention, much advancement in the solar modulation physics, because all the recent data have long observation and time-dependent measurements, and to see how the spectra evolves with the evolution of the solar activity. This is true for experiments in space, and in particular also for the spacecrafts like ACE, that from the end of the 90s is still running and providing us monthly data on the spectrum of cosmic nuclei in the very low energy region. We have interstellar data, I mean, spectra from the interstellar space in the low energy part from Voyager, which have been very, very useful for modeling the local interstellar spectrum. And it's shown in this picture, where all the points are measurements from Voyager. So essentially all species from hydrogen to nickel are measured with and these are outside the heliosphere, so they don't change with time, and they have been very useful to build the local interstellar spectrum, and they give very tight constraints. Regarding the time-dependent measurements inside the heliosphere and close to Earth, here I show the daily measurements of the proton flux by Pamela from 2006 to 2014 at different rigidities. Every color is different rigidity here, from 0.4 GeV to 30 GeV, and similar made here in the right from AMS. Here is the daily helium flux from 2011 to 2020 at different rigidities. It's very interesting to study this evolution and to how it's connected to the evolution of the solar activity and to the solar modulation mechanism. It's important that along with these measurements, we have measurements of positron to electron ratio and the measurement of maybe we'll have measurements of antiprotons. So how to study the charge sign dependent modulation effect is after a long time where there was several speculation on these effects. We have a lot of impressive time series to start with. Then I will switch to the antimatter before concluding and show some results. This is new since 2008. We know there is an excess in the positron spectrum. Here is the positron flux multiplied by E cube, and it's striking the excess of the data in comparison what we expect from collisions. There are many uncertainties, of course, in the background from the collisions, but in any case, the excess is so huge. It's that we can talk about positron anomaly and some extra source. Now, if we look at the electrons, the excess is also inside here. This is the all electron spectrum, so it's electron plus positron spectrum. This is experimentally to be better investigated because there is essentially the data groups in two groups, the AMS and Calet group, and like the red and black on one side, and the other side the Fermi and Dampe electron spectrum, which has they are harder if we see from the flux, and there is a discrepancy that should be clarified. But all the measurements agree that at the TeV region there is a softening of the electron spectrum, the origin of which is to be clarified. Both electron and the positron spectrum agree in the presence of an excess with respect to the background. The interpretation of this excess in terms of dark matter is not convincing at all, because it would require a very strong annihilation cross-section for dark matter annihilating into muons or electrons and large mass. The annihilation cross-section is too distant in some sense from the one required by the cosmology, the thermal cross-section, and not compatible with many bounds. If here I show other bounds from Fermi and from the gamma rays and from the CMB and even from antiprotons, and essentially it's hard to account for description of the positrons in terms to dark matter. It should be, we should think to a leptophilic dark matter with very strong annihilation rate. If we switch also to antiprotons, there is a measurement. We can talk about an anomaly. We can maybe talk about an excess. It's unclear, but it's surprising that the antiproton spectrum at high energy is essentially as hard as the proton spectrum, while we expected to be much softer because it's for secondary production. And also maybe a coincidence, but positron, antiprotons and proton spectrum for a large range of energy at high energy, they have the same slope, and it's puzzling. Here is what we can see if we compare this this hard behavior with the standard and previous propagation models that are based on boron to carbon. So there is apparent excess. Actually, in many work, this hard antiproton to proton ratio prompt the models to produce harder secondary production with some better tuning of the parameters. And it's curious, but there is a very nice room for an excess in the low energy part. And several works agree with the nexus in the 10 GeV part, which is not so visible by eye, so apparent, but it's there and statistically significant, according to many authors, that have actually an interesting interpretation in terms of dark matter, because this excess can be explained by WIMP-like dark matter with the mass at the scale of 50 to 200 GeV, and with the annihilation cross-section perfectly compatible with the thermal level, and also with the Fermi GeV axis. So it's very welcome interpretation, but should be, of course, proven with the other messengers, because the signal is ambiguous with the only antiprotons. It's very interesting to use antinuclei for this search, for the search of new physics access in general, because for the mechanism they are produced like antideutrons or anti-helium. Any access from dark matter induced from annihilation of dark matter would emerge with respect to the background more easily because of the kinematics of the antinuclear production. Here is just calculation, because there are no antinuclear observation of the secondary antinuclear flux, left antideutron, right antihelium, and in comparison with the model, which is actually consistent with the a dark matter model consistent with the antiproton axis. Means if in the antiproton we have a tiny signal, not emerging over the background, but only giving a room to be interpreted in terms of dark matter, we have here the emergence of a strong signal we would have. But this is just an illustration. It's interesting, in any case, to have measurements, even upper limits in this in antinuclei, antideutron, antihelium flux. For the moment, from AMS, we have nothing reported. Antihelium candidates are under analysis, and anti-deuteron search is ongoing, but there are interesting projects. What's the time? I just go fast through the projects. It's very important, this GAPS, the general antiparticle spectrometer. It's very interesting experimentally because it's antimatter spectrometer, not based on magnetic spectrometry, but in the production of the exotic atom with the antinuclei that are absorbed in the detector, and then they eventually produce X-rays and pions. And this is sensitive in the low energy region, which is the region where it's the interesting region for the search for excess. And GAPS will have balloon flights starting from next years, and with the 3 flights, it will be competing. Interesting also another balloon project, the Helix, to measure essentially designed to measure the isotopic composition of light nuclei. Very interesting for what we expect for the beryllium-10 to beryllium-9 measurements. Here is the PAM project, another small spectrometer but for space, and mostly designed having in mind the idea of having a onboard monitor for the radiation, like for long-term missions, because this instrument could be modular and very compact, and could be also able to do physics like magnetic spectrometry and the antimatter detection. Another very interesting project is the Tiger ISS. So from the legacy of Tiger and Super Tiger, it's aimed at measuring up to lead and even more. We have here a projection of the counts for one year operation in the ISS, and it's very interesting because it's the only instrument that is devoted to measure such a heavy component of cosmic rays. The hard experiments in the Chinese space station is planned to be the very first big science experiment in the Chinese space station, and it's a big calorimeter, essentially for measuring electrons and nuclei with the high precision and reaching the knee with direct measurements. Then for the big future, for the far future, I can mention Aladino. It's an idea for a new generation of magnetic spectrometry that where the powerful part is the design in order to maximize the acceptance, to have a 4 pi calorimeters getting particles from every direction, and a tracking system which allows to reach a large acceptance and large maximum detectable rigidity. Here is a projection like for the anti-deuteron flux, which is sensitive only not only to a possible signal but to the background. So should be sensitive to anti-deuteron, so for sure. And more even more ambitious, the AMS 100 project on L2 for with very strong capabilities. I invite you to give at the to look at the white paper for other details. And just to put where these experiments are located, we can represent in this plane exposure time and acceptance. And we fix for these projects 3 years of exposure time. We see how they reach very strong level of collecting powers thanks to the large acceptance, where all the other groups in the left is the existing experiments for like MS 10 years already reached, and Calet, Dampe, and ISS screen. So I think I've done also with the time. The conclusion. With all these new measurements, recent measurements, and we have essentially a lot of new anomalies. So it's hard to fit everything, to make sense all this data into the paradigm we know. Maybe a shift, another approach will be necessary. What is clear is, and it's impressive, is the quality and quantity of so many data that we collect in the last years, and the several unexpected feature. Every new precision measurement is an unexplained feature. For that's how we are going. I really think our next big milestone is the detection in the future of antinucleates. What I hope to see, because it's our gate to the new physics. Here, I thank you, all of you, for the attention. Thank you.
Thank you.